Hi there, in this video we're going to start discussing the area problem. So we're entering chapter 5 and one of the questions is, what does the area represent? Which area? The area under a curve. And so to kind of start posing the problem, we are going to look at what if, when we talk about what does the area represent, meaning the area under the curve, and the curve is velocity. So when we have here, I have the graph, and the x-axis is representing time, and the y-axis, we have been used to the y-axis is the position function, but in this case, what if the y-axis represents the velocity function? So what we have graphed here is the velocity against time. So as time passes, what's the velocity doing? So for this function, y equals 2x, right? Essentially, the velocity doubles the time. So when you have 4 seconds, the velocity is 8 meters per second. So now what does the area give us? What does it represent? And this is a triangle, right? So then let's look at what is the area of this triangle. And we'll use our units to see what we get when we find the area. So the area of a triangle is 1/2 base times height. And so for this particular triangle, we can say, well, the area is 1/2 the base, which is 4 seconds, right? The velocity is given in meters per second, so and this is time, so we're going to say time in seconds here. And so it's going to be 4 seconds is our base. And what about the height? Well, the height is 8 meters per second. So the height here is, we're going to say 8 meters per second. So when we multiply this out, notice that our units, I'm going to have seconds divided by seconds. Those are going to cancel out. So we're just going to get 1/2 times 4 is 2. 2 times 8 is 16 meters. So what does this give us? It's giving us the distance. So essentially, when our curve represents velocity or the rate of change and then against time, when we find the area under the curve, what we are getting here, the area is essentially the distance traveled by the object, whatever that object is. And so in this next chapter, in chapter 5, we're going to be talking about the area under the curve, given that we have graphed the rate of change. So we're going to be graphing the rate of change of a function and then trying to figure out, well, what is that, essentially, what is the distance, or what is the position, the change in position by the object, if what we have is the velocity, the rate of change, or right, the derivative. And so by looking at the area under the curve, we're going to be able to find all kinds of information about a function that we might not know. So here we're graphing the rate of change, the velocity, and when we find the area under the curve, that actually gives us the distance traveled by an object or a particle, whatever it might be. And then as you get into, so this is Calc 1, as you get into Calc 2, and we have more tools to find the area under the curve, you're going to start doing applications of where this is used. But just to give you a preview of coming attractions, it's used a lot to find, like in physics applications, finding force, finding work, and finding volumes, and finding this is going to be really, really useful, finding the area under the curve. But there are lots of useful applications that you'll learn in Calc 2. So how do we find the area under the curve when it's not so nice, right? Like here we have a nice line on an interval, so I was able to create a triangle, and then the area under the curve is just the area of the triangle. But what if my curve is not a straight line, right? What if I have something like the square root of x? So let's look at that next example. All right, so in this next example, so I'm going to use this function on this interval to kind of develop the idea of approximating the area under a curve, given that y equals the square root of x as our curve here. Then we want to approximate the area under the curve on the interval 0, 4. So that means we want to be able to approximate this area. And so notice that this is different than having a nice triangle. I know the area of a triangle is 1/2 base times height. Here, I don't have that luxury to say like, oh, I don't have a shape for this, right? I could try to approximate it with a triangle and then see what it does, but we're going to approximate with rectangles instead. So we're going to use rectangles to approximate the area. Why rectangles? The area of a rectangle is length times width, or sometimes we can also think of it as the base of the rectangle times the height. It's a little bit easier, right, to think of a rectangle than having to use, say, triangles or trapezoids or any other geometrical shape. We want to use a geometric shape that we can find its area fairly easy and then use that to approximate the area under the curve. So here, if I use, let's say, using just one rectangle, is that going to be a good approximation? We know the area of a rectangle, we just said, is base times height. So using one rectangle, what will that look like if I use one rectangle? Let me draw it in green over here. So if I use one rectangle, that means that as I extend it over here, it's going to land, whoops, right there. So I'm going to have a huge over approximation, right? So my area using one rectangle is going to be the base, which is 4, times the height, which is, how high is that? That's 2. So times 2. And remember, if we have our units, this is a rate of change. So whatever the units here are, right, if it's meters per second or inches per minute, then this will be minutes. So you're just going to get a distance. So this will be 8 and then a measure of distance. But this is an over approximation. Can you see why this is an over approximation? We have this extra, the green area that is not part of the area under the curve, right? That's above the curve, so this will be an over approximation. So what happens then if we increase the number of rectangles? So what if we use 2 rectangles instead? So what does our area then look like? And let's say 2 rectangles of equal length. So essentially I'm going to split the interval in half so that I can have 2 rectangles. So I'm going to go over here and then drop down. That's 1 rectangle and then 2 rectangles. So I have this. So I have A1 and A2. So that means that my area approximation for the area under the curve will be the sum of A1 plus A2. We still have rectangles here, right? So our area of a rectangle is still base times height. So what is the base of each of these? That's 2. So same length. So the area for A1 is going to be the base, so 2 times. Now what's the height? When x is 2, what's y? So y is the square root of x, so that means this is going to be the square root of 2. So it'll be 2 times the square root of 2, and then plus 2, the base of the second rectangle, times the height. What is the height of the second rectangle? This is still 2, right? The square root of, when x is 4, that gives us the square root of 4, which is 2, so it'll be times 2. And so this gives us now the area. So I'm going to have 2 root 2 plus 4. So notice that it's smaller now than 8, but it's still an over approximation because I still have this area above the curve. So I'm still getting an over approximation. I could have drawn my rectangles differently, right? I could have had instead go underneath, so from the bottom. And so that is a different method. So here I'm using when I touch the curve, notice that this is the right endpoint that I'm using from right from the interval from 0 to 2. I'm using 2 for the height, so that's the right endpoint. On the interval from 2 to 4, I'm using 4 for the height, so that is on the interval 2 to 4, that's the right endpoint. So I could have done it a little differently by saying using the left endpoint, and that would give me an under approximation, but we'll talk about that as we continue adding rectangles. So what about so using 2 rectangles, notice that I got closer to the actual area. So what about using 4 rectangles? So you kind of get the idea where we're going, right? And we should say of equal length, meaning the base will be the same. So if I'm using 4 rectangles, what does that look like now? So with 4 rectangles of equal length, that means that we want to split up our interval 0 to 4 into 4 equal parts. So that will give me then 1 rectangle here, 1 rectangle here, 1 rectangle here, and then our last rectangle. So notice now that the over approximation area is what I'm shading right now. That is a lot smaller than when we had 2 rectangles, and even when we had 1 rectangle, so it's way better. So then the more rectangles that we use, the better, the closer and closer we get to the actual area, so the better the approximation. So the area here under the curve then is going to be the sum of the 4 areas of the 4 rectangles. And so what are each of these areas? So notice that since we had to break it up into 4 equal pieces, and my interval is from 0 to 4, so that means that the base of each rectangle is 1. And the height is based on what those are, right? So this is 1, that's 2, so this is 3, and then 4. So my area then is going to be the base of each rectangle, which is 1 times the height of each rectangle. So all of these have a base of 1, so I can just put that in. And so really I just need to find the height. And so the height for the first rectangle, when x is 1, the height is the square root of 1, which is 1. So it's also 1. For a 2, the height is given when x is 2, right? That's what I'm using as my height there. So that will be the square root of 2. For 3, the height is the square root of 3. And then for the fourth rectangle, the height is given by the square root of 4, which is 2. And so when we compute this out, we're going to have 1 plus root 2 plus root 3 plus 2. So the area will be 3 plus root 2 plus root 3. These are not like terms, so don't make the algebra mistake of saying, oh, that's the square root of 5. You cannot add the insides. So we can just leave it like that. But notice that our over approximation, trying to say our and over in the same sentence is kind of hard. Our over approximation got a lot smaller now. And so this is the idea. So what if I do it with 8 rectangles? What do you think is going to happen? Right, it's going to get even smaller and smaller and smaller. So the idea is, what if I use n rectangles? So approximate the area under the curve using n rectangles, where n is a positive integer. So essentially I'm going to redraw my curve and then try to put n rectangles in there, and we'll see what the area becomes. All right, so I have drawn my n rectangles here, so that means that you have a1, a2, a3, and so on until you have your last rectangle, which will be a sub n. So what will the total area be? And so this will be an approximation, right? So it'll be a1 plus a2 plus a3 plus dot 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 all the way to a sub n, because you have n rectangles. So if I want to split it up into equal parts, then my interval from 0 to 4, how do I split it up? So I want to take essentially the difference, right, the length of the interval 4. So my this, we're going to call it delta x. So all of them will have delta x, and we'll figure out how to find that. So in here, the area approximation will be the area of a1, so it will be delta x, the base, times the height, which will be f of x of 1. Right, if I split it up into n equal pieces, and then plus the area of a2, which will be my delta x times f of x of 2, plus delta x, the base, all of them will have the same base, times f of x of 3, and so on, plus delta x, f of x of n for the last rectangle. So what do they all have in common? They all have the delta x. So delta x, we can factor it out, and it will be f of x1 plus f of x2 plus f of x3, and so on. F of x of n. So how we're finding our height. So remember when we did, going back to when we had 4 rectangles, right? The base of each rectangle was the same, was 1, and then the height was, so my x of 1 was 1, my x of 2 was 2, my x of 3 was 3, x of 4 was 4. Here, when I had 2 rectangles, my x of 1 was 2 and my x of 2 was 4, because I only had 2 rectangles. And so with x of n, this is what it will look like. And your delta x, so how do I find delta x? As I was saying earlier, is the length of the interval. So in this case, it's 4 minus 0 over the number of rectangles. So in more general terms, on an interval a to b, the base then will be, your delta x will be b minus a, the length of the interval, over n, and n is still the number of rectangles used. And b minus a is the length of the interval. Right, so if I wanted to find the area or approximate area under some other curve, say y equals x squared minus 2x on the interval 2 to 8, oops, closed, using say 6 rectangles, what will my delta x be? Right, then delta x will be the length of the interval, so it'll be 8 minus 2 over the 6 rectangles. So in this case, 6 over 6, which will be 1. So then you will go and figure out what the area might look like. So because it's the interval from 2 to 8, you will go to 2 and then all the way to 8, and then you will apply your delta x. Delta x is 1, so that will be 3, 4, 5, 6, 7 until you get to 8, and then right, whatever the function looks like. So this is just an example. How do you find your delta x? And then the area is the sum of all those rectangles. So if you're using 4 rectangles, 6 rectangles, 8 rectangles, 12, that's getting a little out of hand. There's a lot of rectangles to use. So now here, in my examples here, I was using the right endpoint, which was always giving me an over approximation, right? So this is using the right endpoint. So it gives me this, and so this is an over approximation. Again, how do I know that this is an over approximation? Well, I can tell from the graph because I have this little pieces of the rectangle that are above the curve. So that means those little areas are being included in this calculation, and so because they are above the curve, that is giving me an over approximation, right? Because I'm looking for the area under the curve. So what if I use the left endpoint? What will this same one look like using a left endpoint? So let's do the left endpoint for this same example. All right, so here's my picture again. So we're still going to do area under y equals root x on 0, 4, the same interval, but now using the left endpoint. Using left endpoint and still 4 rectangles. So notice that now using the left endpoint, so that means I still break up my interval into 4 equal pieces, but now when I say using the left endpoint, that means that the left endpoint gives the height of the rectangle. So that means on the interval from 0 to 1, the left endpoint is 0. So notice that now there's no rectangle there. And then on the interval 1 to 2, the left endpoint is 1. So that's where my rectangle starts. And then 2 to 3, my left endpoint is 2, so that's my rectangle. And then 3 to 4, my left endpoint is 3, so that's my rectangle. So now notice that we have an under approximation, because now the rectangles are completely under the curve, and so these little guys that I'm shading are parts of the area under the curve that are not going to be included in our approximation. So the area is approximately, we still have A1 plus A2 plus A3 plus A4, but the way that we find the height is different. So our base is still 1, so our delta x is 1. So times the height. Now the height here using the left endpoint is given by, on 0 to 1, it's 0. And then my second, so essentially A1, there's no rectangle there because there's no height. And so this is my A2, A3, and A4, right? And that is my A1, which is really no rectangle because the height is 0, because we're using 0 as the endpoint for the height. So then the height of the area of the second rectangle is base, which is 1 times height. The height is given by, in the interval 1 to 2 is 1, so the square root of 1, which is 1, plus the base of A3 times the height of A3. The height of A3 is, I'm using the left endpoint, so 2, so it'll be the square root of 2. And then plus the base times the height of, on the interval 3, 4, I'm using the left endpoint, so 3, so it'll be the square root of 3, right? And essentially, and maybe I should have written it the way that I wrote it above with n, so this should be approximately, so as your delta x times f of 0 plus delta x times f of 1 plus delta x times f of 2 plus delta x times f of 3, right? Your x1 in this case is 0, your x2 is 1, because we're using the left endpoint. And so then that gives us this guy. So we can say the area then is approximately 0 plus 1 plus root 2 plus root 3. So we just get the area is 1 plus root 2 plus root 3. So this is an under approximation, because again our rectangles are give us, so those little gaps under the curve. So between the rectangles and the curve we have those little gaps. And so looking at the back at when we had it with 4 using the right endpoint, notice that we had 3 plus root 2 plus root 3, and this was an over approximation. Then using the left endpoints we have 1 plus root 2 plus root 3, and this is an under approximation. So that means that the actual area is between those two values, between the under and the over approximation. So what I can say is that then the actual area, so 1 plus root 2 plus root 3 is less than the actual area, and that's less than 3 plus root 2 plus root 3. So I essentially found a lower bound and an upper bound for the true area under the curve. So that's what I know. And so notice that if I increase the number of rectangles, so if I go to 8 rectangles, then I can do my left endpoint and get an under approximation, and then I can do my right endpoint and get an over approximation, and that will put me closer to the actual area. So this is my left endpoint, and this is my right endpoint approximation, and so the area is in that manner. Now, this is not always going to be the case that the left endpoint gives you an under approximation and that the right endpoint gives you an over approximation. It really depends on what the curve looks like, right? This curve is an increasing curve, but if my curve was decreasing, then the left endpoint would actually give me an over approximation and the right endpoint will give me an under approximation. But the idea is that the actual area lies between those two. A better approximation will be what if I use the midpoint? If I use the midpoint, then that cuts down the over and under approximation by quite a bit. So in the next video, we're going to do an example where we find for a different function, and we're going to do right endpoint, left endpoint, and midpoint area approximations.